So, hello everyone. Thank you again, Stacy, for the invitation and for the introduction. I like to joke that I started with asteroids that are near the Earth, and I've just been going farther and farther away, and I'm not even in the same solar system anymore. So it's been an interesting journey, to say the least. But today, or tonight, we will be talking about cryovolcanism and what it is, what it might be, where it is, and how it could work based on what we think we know so far. So first, let's ask the question, what is cryovolcanism? And quite simply, it is exactly what you would imagine if I told you, oh, it's an ice volcano. You might imagine something like the classic conical shape of a with the point at the top and something oozing out of one of its out of the top of it, or maybe along the side. You could imagine that there's something cold, but still flowing, still rich in volatiles, meaning gases. So something is happening. Keep that image in your head. We think, based on what we have seen so far, not just of Pluto's moon Charon, or Charon, or Charon. I've heard it pronounced many different ways. For consistency, I will just be saying Charon tonight. So we have looked at moons beyond and including Charon, and we've seen what looks like this smooth material over the surface. What we're looking at here on my screen right now, if you look at the bottom part, so here's a ridge in between. It kind of cuts the part of Charon that we saw. It cuts it almost in half, which is very convenient for us. We call the part in the north the Oz Terra, and we call the part in the south Vulcan Planitia. If you are a Star Trek fan, that is exactly what it is named after, the Vulcans. And we look at Vulcan Planitia and we see that maybe it's a bit smoother than Oz Terra. It definitely looks like it has a different texture. Usually when we see this resurfacing on any other rocky moon, we say, oh, it must have been volcanically resurfaced. Well, here we're saying the same thing might have happened, but with an ice volcano instead of a rock volcano. This screen actually shows a bit better what I was saying. Before we were just looking at the raw image. Now we have a bit of annotation here. There's a couple of chasma or chasmata, Manjet chasma, Serenity chasma. We also have these two features, Clark and Kubrick Montes, and they will have better pictures of them later on, but they look like they're mountains surrounded by a moat. So is that moat cryovolcanic in origin? And if there was cryovolcanism on Charon, when did it happen? How did it start? Thanks to the New Horizons mission, we do have more information than we've ever had before because we have good images, and we also have chemical data about the surface that we've gotten from the New Horizons mission. But it's not enough because it turns out we still have a lot of unanswered questions about cryovolcanism. But I might have gotten ahead of myself a little bit because I've been saying that cryovolcanism is weird, it's different, we don't understand it, but I haven't explained why. So to answer all of these questions, first I'm going to explain regular volcanism so that when I tell you about cryovolcanism, you can understand for yourself exactly why we are so confused about it. So regular volcanism is it's the extrusion or expulsion of hot rock, a hot or molten rock or ash material. It can also have those gases, those volcanic gases also come up. So we have the same kind of process in cryovolcanism we think, or in volcanism we think is active in cryovolcanism. And volcanism is by itself a process to help a planet get rid of heat from its interior. Now, I like to do an analogy when I give this talk to little kids because they think it's hilarious. But what happens to your bodies when you exercise or even when you go outside on a hot day? If you are thinking to yourself, well, you sweat, you are 100% right. So your body's internal temperature is too high. Your body sweats to help cool it down. And a planet is kind of doing the same thing. So if it helps you to think of lava as a planet's sweat, then that's exactly what it is. It's an analogous kind of process. It's just the planet trying to cool itself down. But because of the heat and the heating requirements that are necessary for volcanism to begin, we only see volcanoes on solar system bodies more than 600 miles in diameter. So you have to be a pretty big planet before you can have volcanism. And the third thing I want to carry forward is that on Earth and in other terrestrial or rocky bodies, volcanism is driven by buoyancy. So the rock is melted, it's less dense than the solid rock, so it rises up through Earth's mantle and the crust until it reaches the surface. We don't have the same thing to happen in cryovolcanism, and we can talk about why that is later, but remember that density is a big part, that it's a big driver of volcanism. So here's what some volcanoes look like on other planets. On the previous slide, we saw a picture of a volcano in Hawaii. On the left, what we're looking at in this Viking 1 composite image is the largest mountain slash volcano in the entire solar system. It is called Olympus Mons. It's on Mars. It's 2.5 times as tall as Mount Everest. It's 370 miles wide. So this is a massive, massive, but no longer active volcano in the solar system. What we have in the middle in this more orange picture is a picture of volcanoes on Venus that was taken by the Magellan spacecraft. These are volcanoes on Venus are also called pancake domes. So they weren't able to grow very tall because Venus's atmosphere is so thick, it actually puts a significant amount of pressure on even a volcano so that it can't grow up, it has to grow out. So that's why these look so flat and wide. They are actually called pancake domes or pancake volcanoes. So I always get a kick out of that because I mean, I really like food. So it's kind of fun to make Venus volcanoes instead of pancakes. And finally, in this smaller image, this is it's actually a GIF of, so if you look closely at this pimple at the top of it, you'll actually see it's moving. That is a plume called Tvashtar on the most volcanically active body in the entire solar system. This is Jupiter's moon Io. It is the closest of the 4 major moons that Jupiter has. And the plume itself that you're looking at in this little image is 200 miles tall. So it gives you a sense of scale for how big the rest of the moon is. But what controls volcanism and how come things are so different on different planets? Well, first, of course, there's the planet variables themselves. There's gravity, atmosphere, bulk composition, so what the planet is made out of. We also, and we'll come back to talking about heat budget. There's also the properties of the magma itself. How hot is the temperature? How dense is it? How viscous or how sticky it is? Is it more runny like water or is it very sticky like honey? And that will affect how the lava flows and how long an eruption can last. We also want to pay attention to things like how many gases are in it and what the crystal or water content is. It's really complicated how all of these properties, including the eruption rates and just the shape of the volcano itself, can contribute to the diversity in volcanoes that we see, not just on Earth, but across the solar system. Now, I talked about the heat budget very briefly earlier, and it ends up being very important because a heat budget is a direct link to how much volcanism a planet can have. Something with a high heat budget like Io has a lot of volcanic potential. But something like Mars that doesn't have a lot of its own heat anymore, we're not going to get another Olympus Mons. We have the one, and that is it. So what are sources of planetary heat? Where does all of that heat come from to create that planetary sweat? The first and potentially most dramatic comes in the form of accretion, which is the initial beginnings of a planet. It's when the dust and gas first comes together. What we're looking at here in this image, those rings that you see in this, we're actually looking at a baby solar system here. So in the center is the star, and the rings that you see around the star, we think, or the interpretation of these rings is that those are places where a planet is forming. So it's taking all of the dust and the gas that's in its way and it's condensing it into a sphere or some kind of spherical shape. And that is the process of accretion. That is how planets are born. And every planet will begin with some heat just from that process of accretion. Ooh. And then the next one, which you get only if you are a large enough body, planetary body, is this process of differentiation. That's the process where different layers are formed in the interior. So it's how we get the core, the mantle, and the crust. All of the heavier stuff goes to the bottom. So things like iron and nickel will go into the core. The very light things like aluminum generally end up on the crust. And then things like magnesium, silicon, and some iron will end up in the mantle. That's the middle section. So this is just an illustration of what that process looks like. Of course, it's very much sped up. Something that is a much more long-lived source of heat, and it's something that Earth benefits from, is the presence of radioactive elements in its interior, and then over time, that radioactive decay of those elements. That's a major, major heat source. And again, it's only some of the largest bodies that have enough of those radioactive elements that they got during their accretion process that they are still warm today. So that is why Mars is cold and Earth is still volcanically active. It's because of these radioactive elements. And then out in the far reaches of the solar system, where we don't have as much rock, but we have a lot higher concentrations of different ices, not just water ice, but methane and nitrogen and carbon monoxide ice, we have something called tidal flexing. Tidal flexing is it's the most important source of heat in the outer solar system. And to explain it, I'm gonna have to use my hands a bit. So imagine Jupiter is over here in maybe off of my screen, and we're looking at Io, so the little very volcanically active moon, and it's going around Jupiter. So I guess Jupiter is actually here. So imagine it's going around Jupiter. It's so close to Jupiter and Jupiter is so massive, it is exerting gravitational forcing on Io's crust. It's actually deforming Io. All of that deformation, especially in an orbit that's only about a day and a half. It's a very quick orbit. But all of that flexing is producing, all that friction is producing a lot of heat. That heat in the interior is expressed as volcanism. So what we have in summary is that accretion and differentiation, they generally only happen once in a planet's lifetime, and they're relatively short-lived sources of heat. But then radioactive decay and tidal flexing are much more sustainable sources of heat. And that's what we think is driving most of the volcanism or cryovolcanism that we see active today. How am I doing?
Great.
Okay, cool. Moving on. So now that we have a basic understanding of volcanism, let's move on to what happens when we start adding large amounts of water to this volcanism. And as you might expect, a planet that has a lot of water is an ocean, or we call it an ocean world. So Earth is an ocean world. We have a large amount of this surface water Europa is also an ocean world, even though it doesn't have surface liquid water, it has it underneath this ice shell. We know that that ocean is there. We know that it's global. We think Europa actually has more water than all of the Earth, which is wild to think about. Europa, for context, is only about the size of our moon. So Earth's moon, can you imagine Earth's moon having more water than Earth itself? That's what Europa is. And then going even farther out to Saturn, we have the moon Titan. Titan has water, or might have water very, very deep in its layers, but it's cold enough that on its surface, it actually has liquid methane. And just like we have a water cycle here on Earth, Titan, we think, has a methane cycle. We can actually look at images of its surface over time, and we see the size and shapes of different lakes on Titan changing. So it's a dynamic place, it's a dynamic surface. And we're really excited to be going back there with the Dragonfly mission that will hopefully launch in 2028. So, as you can imagine, places that have liquid water are probably and are warm enough and are big enough are probably places where we might see some evidence of cryovolcanism. Of You can imagine that the connection between liquid water and an ice volcano is probably very strong. So let's advance. There we go. So going back to Europa, I've already said that it's about the size of our moon. It's an ice shell over a thin global ocean. We think that the ice and the water layer together is only about 100, let's see, it's 160 kilometers. I think that makes it about 110 miles, somewhere around there. So it's really not that much. It's more than Earth, but it's not as much as it could be. Europa is also one of those places where tidal flexing is very important because it orbits Jupiter every 3 days. And Jupiter being so not quite as fast as Io, but Jupiter is so massive that it's always deforming Europa by about plus or minus 30 meters every orbit. So that's a lot of friction that's generated. We think that's a big part of why the ocean has remained liquid for Europa's entire lifetime. But we've already talked about Titan a little bit too. It's not the only place in the Saturn system that is cryovolcanically active. We have Enceladus, which is one of the smallest moons in the solar system, and yet it is incredibly active. It has these beautiful plumes that come out of its south pole from a region that's called the Tiger Stripes. They're really stunning. And the Cassini mission, which ended in 2017, was able to actually fly through some of these plumes to get information about what the composition of the ocean on Enceladus is. They were looking for any kind of signs of life, amino acids, I think. I think they found that, which is really exciting. Going back to Titan though for a second, because I love the name of one of these reported cryovolcanoes, it's Doom Mons. If you have noticed that there is a bit of a science fiction slash fantasy theme going on with the names in the outer solar system, you are 100% right. We are all very we scientists, we love our classic sci-fi fantasy literature, and we're just trying to honor it in what we name these objects. So we have Doom Mons on Titan that is almost a mile tall and 37 miles across. Maybe I wouldn't want to be the Hobbit to go visit Mount Doom, but maybe one day somebody will. Maybe a human will go. Of course, we are moving farther and farther out from the sun. We have, unfortunately, we only have one set of images from both the Uranus and Neptune systems. But it was enough to intrigue us into saying, look, there might be more evidence of this smooth terrain that might it might be recognizable as a cryovolcanically resurfaced area. So something where there was a great expulsion of cryomagma or cryolava on the surface, and then it just froze in place, and it was almost like a lake that got frozen in place. That's what we think might have happened. So we see a lot of evidence of cryovolcanism. We haven't ever witnessed it happening. And we also have an issue, as I have alluded to before, but I think the next slide is going to introduce, here we go. So I say that cryovolcanism is a fundamental process that we don't understand. We do see a lot of evidence for it in different places in the solar system, but when we think about how it works or when it works in a planet's history, we're a little confused. And here's why. Remember when we talked about volcanism and on terrestrial volcanism, and we said that it was driven a lot by buoyancy. In cryovolcanism, liquid water is more dense than solid water. So we don't have that buoyancy benefit that we had with the rocky volcanism. So there has to be another process, literally pushing out that cryolava in order for it to work. Otherwise, there's no reason why the water on the bottom should want to be on the top, on the surface. So there has to be something pushing, and we think we know what that was on Charon. We're hoping we can figure out Charon and use it to study all of these other places and figure out how cryovolcanism might work. So again, we have the question of how does it work when we are confronting that buoyancy issue? But more than that, what is a typical cryomagma? What is it made out of? How much water is it versus how much ammonia is it? How sticky is it? That viscosity component. Is it strong enough when it's formed to build large cryovolcanoes, or would they actually kind of end up more like the pancake domes that we see on Venus, even in the absence of a heavy atmosphere? How much cryolava could be released? And how often can that happen? We don't know yet, but we're working on it. So, we are working on it because we have good images of Charon from the New Horizons spacecraft. The spacecraft itself, that's an artist's image in the leftmost panel in the middle. We actually have a composite image of Pluto, not Charon. So Pluto is the one with the nice, beautiful heart. The heart area is called Sputnik Planitia. So Sputnik, of course, being a reference to the first spacecraft. And then in the third panel on the right, we have maps of 4 different ice concentrations on Pluto. We have methane in purple in the top left, nitrogen ice in yellow in the top right, carbon monoxide in green in the bottom left, and water ice in the bottom right in blue. So this is showing us that there is an abundance and diversity of ices that we can take into account when we're trying to figure out exactly what a cryolava on Charon or Pluto might be made out of. And we really care about ammonia, which I don't have a map of, but ammonia, think of it as like the antifreeze that you put in your car. Ammonia can be a very important way that the cryolava stays warm enough to flow at all, so that ammonia kind of makes it more, it makes it flowable. I don't think that's a word, but I hope you understand what I mean. So when we talk about Charon, here are some basic facts. Charon is smaller than our moon, actually, and it co-orbits Pluto. So it does not, usually there's a system like Europa orbits Jupiter. These two kind of co-orbit each other, so they're both exerting tidal flexing on each other, which is an odd and different system that we haven't explored yet. But we know from its overall density that it must be a mixture of ice and rock. So there's definitely enough water and other kinds of ices that we could have a large cryovolcanic flow. And we also know that there is ammonia on its surface. So already we're thinking, aha, ammonia can make things flow at lower temperatures. Maybe that is what happened here on Charon. So we come back to that map that we saw earlier, and now we might look at it a bit differently because now we're seeing places where there might be evidence of cryovolcanism, and it could even be recent. We also can see a clear difference between the northern Ozterra, which appears to be blockier. It definitely has a different texture from the southern Vulcan Planitia, which, while they both have craters, it looks like Vulcan Planitia has smoother terrain. It's much crisper terrain too. If you look at the craters themselves, they look a bit cleaner, a bit newer in Vulcan Planitia. So that could be a hint at some relatively recent geologic activity. Let's look at the two mountains in a moat. So we have Clark Montes over here and Kubrick Montes, again, the nods to science fiction. We see these as mountains that are surrounded. So first they are depressed, they're in a depression, but they're still mountains. So they're a bit above the rest of the surface, but if you look at their total height from their depression, they're about 4 kilometers tall. So are these small cryovolcanoes? And is it that the fact that when they erupted, if they could have used up all of the cryomagma that was in a magma chamber underneath them so that the weight of all of the magma on top instead of in the crust maybe depressed the surface. So maybe what we're looking at is actually some crustal deformation as a result of this extra mass. That would be pretty cool. So we're still working on that. We're trying to figure out again, if there was cryovolcanism, how much would be needed, and is it consistent with what we would estimate is present in Clark and Kubrick Montes. And in the right picture, we have what looks like this pitted kind of terrain. We don't have a better image than this, unfortunately, but we think that maybe this pitted terrain could be the result of gases escaping from a cryovolcanic flow. We're not sure, and again, this is as good as we're going to get for a while, so we are still again working on that, just trying to figure it out. So here's what I'm doing, and don't worry, we're almost done. The first thing I'm doing is I'm looking at the clustering of the craters. I'm trying to find areas that might be lower in crater density, and that might point to areas of recent cryovolcanic resurfacing, because the cryovolcanism would have flowed over and kind of filled in the craters so that we wouldn't see them. At the same time, I'm also using a geothermal and geochemical model to figure out what Charon's composition is on its inside, not just today, but throughout its history, and trying to track if Charon ever had an ocean, when did that ocean freeze? That ocean freezing might have been the force that pushed out that cryo lava that led to the resurfacing event that we think we're looking at. So I'm trying to pin down exactly when that ocean would have frozen and under what conditions. And then finally, once we think we understand what happened on Charon, we're going to look at the other places in the solar system that have what we think is evidence of cryovolcanism. And we're going to try and generalize a process to these other places. And again, trying to consider all of the different variables that might affect a cryovolcanic eruption. So my second to last slide is just to tell you all, why does this work matter? Why do I do that, and why should you care? So first, on Earth, volcanic rocks are a way that the Earth actually brings material from the inside to the outside, and that seems kind of trivial, but we don't have the technology to get down to levels or to depths in our own planet where different rocks exist. And knowing better what is inside our planet is going to help us determine not only the history of our planet, but the history of many other planets as well. The ones that are like Earth, the like Mars and Venus and even Mercury, all of these terrestrial planets. We think the same is true for cryovolcanism. It's a way to get stuff from the inside to the outside so that we can look at it better. That's important when we're trying to figure out connecting threads between all of these different planets and moons and why they look the way that they do. We also have I think it's pretty cool, but of course, when an eruption happens on Earth, there's a lot of gas and dust that gets released into the atmosphere. If we are looking at an exoplanet's atmosphere, we need to know if what we're looking at is part of the planet's original composition or if it's being altered by volcanism. So knowing how a planet responds to different stresses, and the heat stresses in most importantly for volcanism, we can figure out what a planet is doing just by looking at the atmosphere, but only if we know what to look for. We also know that and this would be true for cryovolcanoes as well, because there are probably a lot of cryovolcanically active exoplanets out there, and we like to be able to interpret what we're looking at instead of, so that when we're looking for signs of life, we know we can rule out certain volcanic or cryovolcanic signatures. We also know that volcanoes, while they can be incredibly destructive, they are also important for fertilizing soil around the Earth. We know that volcanoes are also a part of plate tectonics. So there's this constant cycling of materials that's happening on this planet. We think it's possible it could happen elsewhere in the solar system, although right now, Earth is the only place that has the plate tectonics as we know them now. We think that this kind of cycling might be necessary for life, or at least the sustainability of life on Earth. So, and then the last thing is to say that when looking for life in exoplanets, we are always interested in water or water-rich worlds. Of course, there's a direct link to cryovolcanism when we're looking at water. So there's a lot of connection there, but we need to know what the water is doing in order to figure out what we're looking at. So this is my final slide. I will invite you all to write down my email address so that, or either one would work. If you have any additional questions that we don't get to tonight, please feel free to email me. But otherwise, I'm going to leave this slide up and I will take your questions. Thank you so much for listening.